Okay, for today's class activities, we're just going to focus on three problems. They're all fairly complex, and we're going to go through them carefully. And so go read chapter 12, sections 8 and 9 carefully, and then go and try your hand at these three problems. Okay, and you can do part A of 65. That's a review problem from an earlier chapter. And we're going to focus on part B for this chapter, or for this reading. So go try your hand at those and then come back for guidance through this video. Okay, on number 31, we're going to apply the ideas of equilibrium or a static situation. This is where nothing's moving. Okay, and the case at hand is we have this 100 kilogram plank that's pivoted on two, or it's not pivoted, it's resting on two points at its endpoints, at the edge of the board. And then standing off center on the board is a person. Okay. So the board has an M and the person has a big M. All right. The board has a length. And the person is standing from this end a distance R. I'm going to call this R1. Okay. Now our goal is to find out what force each of these pivots push up on. Okay. Now, without torque, which is the new material from this chapter, without torque, we could find out the net force pushing up because we could figure out the net force pushing down. It would be the force of gravity acting on the center of mass. I'll call that Fg little m. And then there's a force here, that's Fg big M. Okay, the force of gravity from Earth pulling down on the person, which is a third law pair to the normal force pushing up by the board, which therefore is equal to the force of the person pushing down on the board. Okay, so I kind of used a Newton's third law to jump to this conclusion. So we have those two downward forces, both gravitational forces, pulling down, and then we have these two pivot points pushing up. We have this one, I'm going to call that F right, and this one is F left. Okay, so we have those four forces. And since it's not moving, that means it's not accelerating. And since it's not accelerating, it means the net forces should be zero. Okay, so from that, we can say that these upward forces equal the downward forces, but there's no way to figure out exactly how much is the right force and how much is the left force separately. So that's where torque comes into play. Okay, so think about how you could apply torque to this to be able to solve for this force or this force. Okay, the first thing to recognize is we could say tau net about some point is equal to I alpha, but alpha's 0. So the net torque's about some point is 0. And the beauty of equilibrium problems and statics problems is that nothing's moving. So I could pick any point to be my reference. And so I could choose the rights. I think I got these backwards. I put left and right on the wrong sides. That's right. That's left. There you go. Sorry about that. Okay. So I could choose my point to be right here. I could choose point A to be right here and measure all the distances relative to this one. And if I do, what does that mean about the torque due to this left force? It would be 0 because the distance from this pivot point to where that force is applied is 0. The force is applied at that point. Or I could pick this point to be my reference point and measure all distances to all the forces relative to that point. And in that case, this right force applies no torque because the force is applied at that point. So that's the power of this. Let's go ahead and pick this as our pivot point and then apply this net torque. Okay, so the net torque, I'll go ahead and choose the convention of counterclockwise is positive. We'll see in a later problem that it's your choice to make, but make sure you're consistent. So I'll choose anything that would make this rod go counterclockwise would be positive. Anything that make go clockwise would be negative. So looking at about this point, if this rod were to pivot about that point, this force here would make it go counterclockwise. So that's going to be a positive torque. So I'm going to say Fr, and then times the distance from the pivot point to where that force is. Well, that's the whole distance, d. So I get that torque. And technically, there's a sine of theta, which is the angle, sine of the angle between the radius here and that force, but they're perpendicular because this distance goes from here horizontally to where the force is applied. The force is directly up, so I get sine of 90, which is 1. Okay, but always check that, make sure. Okay, so with that in mind, let's now find the other forces. Okay, so again, I can emphasize I don't need to worry about this one because there is a force, but it's at the pivot point, so the distance is 0, so that would give no torque. So let's look at the other two forces. We have these two downward forces, so they're going to be negative. So I'm going to get a force due to gravity at the center of mass of this 100 kilogram plank. So the center of mass is d over 2. So I'm going to get little mg, that's the force, times d over 2. And that's its distance from a pivot to where the force is applied. And it's also 90 degrees. R is horizontal, the force is down. So there's sine of 90. And likewise, a minus big M times G, and it's this distance R1 away. So those are all the non-zero torques, and because it's not moving and therefore not accelerating, that equals 0. And so looking at this, we know all these other values. We know the masses, we know gravity, we know D, and we know R1, which means we can find this force. Okay, and I'll let you do that. And Fr ends up being 112.6 repeating newtons. Okay. So we have found part of it. Now what about the force from the left side? Okay. How would you do that? Apply the same idea, only now put your pivot point right here so that we can get rid of this one, but include this one, leaving us with just one unknown. Okay, if you do that, you're going to end up with, looking at this way, this one would be about that point, this force would cause it to go clockwise, and these would be counterclockwise. So we'd get mgd over 2, because the center of mass is equally between these 2 points, so it's d over 2, plus big mg. Now the distance from here to this person is d minus r1. Okay. And those are both positive because they would make this thing rotate counterclockwise about that point. And then this one would make it rotate clockwise, so that's a minus FL times D equals 0. So again, we know all this information, and so we can solve for this force, and we will get FL equals 751.3 repeating newtons. Okay. So we've answered the problem. We've found the forces from these individual pivot points, where from doing the net force equals 0 would only allow us to find their sum. Okay, but what I want to say is we could have, if we wanted to, after finding this one, we could have then used net forces to find this other one, because we know that the sum of them must equal the downward forces, and if we already have one, then we should be able to find the other. And so by applying the net forces, we can say that we'll do the upward forces FL plus FR, okay, minus the downward forces mg minus big MG must equal 0. Okay, so suppose when we found FR first, we can find F left. And that's going to be equal to, now these over to the other side, we get M plus big M, G, and then subtract FR. And now if you plug in these values, you'll get this again. So that's the beauty of statics, is you have a lot of information that relates variables, and there's many different ways of going about it. So we could have done torque to find this one and then jumped to our regular Newton's second law, or doing torque with two different pivot points that we get to choose. We'll get the same answer. Okay, so that's something I want you to remember, is think about that. Okay, well, with that, let's move on to 35. Okay, so in this case, we have a sphere rolling down an incline that makes an angle of 25 degrees up from the horizontal. Sphere starts at rest and is moving at the bottom. It's a fairly long incline, over about 6 feet long. It's 2.1 meters. So it's a very long incline, and 25 degrees is not too shabby. And so it's falling through a decent height, which I'm going to choose up to be positive, okay? Whereas I'll choose down to be the distance it travels. Okay. And so we could say things like this has an S0, a Y0, a V0, and an omega 0, because this is going to roll without slipping all the way down this ramp. And then here I'll have an S1, a Y1, a V1, and an omega 1. Okay. Now, note, I'm not worrying about an acceleration in here because I'm going to use an easier one. I'm going to use conservation of energy to do that. Now, because of that, I'm given the length down, so I'm given the S coordinate, but I'm going to need Y. So just to clarify the geometry here, I'm going to draw a geometric triangle representing the problem with that theta. This is delta S, and this is delta H, and they are related as delta H equals delta S sine of theta, because it's opposite over hypotenuse. So the opposite equals hypotenuse times sine of that angle. Now in this case, I'll go ahead and, instead of listing my knowns as I've been doing in the class exercises, or as I've done in the class exercises, let me just go and cross them out here. That's 0. Okay, this is 0, this is 0, and this one is 0. And these are the values I need. So this is really Y0 is equal to S1 sine of theta. Okay, so that's my setup. Kind of got it clear. And now I'm going to apply my main fundamental equation, which here would be conservation of energy. So it's mechanical energy. There's no frictional loss. And so I get K1 plus UG1 is equal to K0 plus UG0. All right. Now, which ones of these are 0? It starts from rest, so that's 0. And it ends up at the ground where I've chosen my axis to be 0. So we can say that gravitational potential energy is turned into kinetic energy. But this kinetic energy is K translational, the motion of the center of mass, plus K rotational, the motion about the center of mass, okay, equals UG0. Okay, so that's kind of the big new thing here, is that we can break our kinetic energy into both translational and rotational, dealing with not just a point object moving, but now this object's rolling, and we care about its size and extent, its radius, and how the mass is distributed. Okay, go ahead and see if you can now solve for the angular speed from this relationship. Okay, so the angular speed is buried inside here, so we need to see how these are related. So first of all, K trans is 1/2 mv squared, and this is the center of mass v. So I'm going to place that here. Oh, I need to put my 1s here. Okay, I'm going to put this 1 here, emphasizing it's the center of mass speed. That's how the center of mass is going. Okay, all right, and then plus 1/2 I omega 1 squared. equals mg y0. Well, what is I for a solid sphere? It happens to be 2/5 mr squared. You can look that up in the table. So we get a 1/2 mv1 squared plus a 1/2 2/5 mr squared times omega 1 squared equals mgy0. You see, the mass doesn't really matter. It cancels out in each term. All right, now the last thing that we need to apply is how is V1 related to omega 1? Because it's rolling without slipping, those have a fixed relationship. Okay, so the question is how? How much? So remember that V1 is equal to R omega 1. Okay, and so we can rewrite this now. Say 1/2 R omega 1 squared plus, let's combine some of this, we get a 1/5 R squared omega 1 squared equals gy0. And notice we have an R squared and omega 1 squared. That's the same as this, so these are the same terms, only with 1/2 and 1/5. So combining that, that's 1/2 the same as 5/10, and this is 2/10. So 5/10 plus 2/10 is 7/10. We get 7/10 R squared omega 1 squared equals gy0. And therefore, solving for omega 1, we get omega 1, multiply the 10 up, divide the 7 down, divide the R squared down, and we get 10 gy0 divided by 7 R squared, all square rooted. Okay. Now, having done all that, we can plug in our numbers, and you're going to get 88 radians per second, which is about 14 revolutions per second. Okay, now let's just do a little test and make sure that's it. Seemed a little, initially when I got that number, it seemed a little high, it seemed a little fast. But remember, the radius of this sphere is only 4 centimeters. It's a pretty small sphere, and it's rolling down 6 feet, 2 meters, 2+ meters length. Okay, and since it's rolling without slipping, there's no losses of energy to friction, and so it's got plenty of time to pick up speed. And the angle of 25 degrees is not shabby either. Okay, so this does seem reasonable. It did seem kind of high to me until I recognized that the radius was fairly small compared to that. So it's going to end up rotating quite quickly. Okay, just to review this one really quick. Important things is we had setup, very carefully designed. We used conservation of energy. Recognize that our kinetic energy is in 2 pieces. And then ultimately recognize for rolling without slipping, the center of mass velocity is related to the angular velocity by r omega. We're able to solve this. Okay, very good. Now let's move on to 65B. As you're looking at that problem, I'm going to draw it up. Oops. Okay. So what we have here is we have one block of mass 1 sitting on a frictionless table. A rope is tied to it around a pulley to a hanging mass. Okay? And we release this mass at rest. Okay? We know that gravity is going to pull down on this, and then this is going to pull forward. We can assume there's no friction in anything, so there's no friction on the bearings of this either. Okay, now, if in past problems, we've done a problem like this. We've done problems like this. But we considered this wheel, this pulley, to have no mass. Okay? And if there's no mass, then the tension on this side must be equal to the tension on this side. Okay, and so we're able to just assume the tension is the same. But now that this has mass, that means in order to get it to speed up, there must be a net torque. You have to have a net torque to cause this to speed up. Because if tau equals I alpha, alpha is non-zero. If these are speeding up, this is speeding up. Okay, so let me write that. Tau equals I alpha. Okay. No matter whether this has mass, this is definitely speeding up if these are speeding up. Okay. But the problem is if there's no mass, then there's no moment of inertia, which means there's no net torque, which means the tension pulling down here is equal to the tension pulling horizontally there. And so we can just say the tension pulling on the box here is equal to the tension pulling on the box here. But now that is not zero anymore. So we can't say that. We can't say that T2 is equal to T1. But we still have this rule that can help us relate the two. Okay, so see if that's enough information to help you solve this problem. Okay, another bit of information that's really helpful is recognizing how the acceleration of this object is related to the acceleration of this wheel. The tangential acceleration along the edge is equal, because if this is accelerating as 1 meter per second squared, then the rope right here touching this edge must be also accelerating 1 meter per second squared. And so the angular acceleration is related to that tangential acceleration by our general relationship. We have A tangential is equal to R alpha. Okay. And so the acceleration of this is related to the angular acceleration of this one. And all three of these have that similar acceleration. So you can say that A1 is equal to A2, and that's equal to AT, and you can just call that all A. Oh, sorry. Let me bring this back into the picture. You just call that all A. All right, see if that can help you now solve this problem. Okay, so in order to make this work, we need to analyze these three things separately, applying Newton's second law to each of them. So if we look at number 1, I look at that, I see there's one force acting on it. I'm going to call that T1, right? Which means that acceleration is this way, A1. So applying Newton's second law in that direction. Oh, sorry, I was doing it in my head, but need to do it explicitly. I'm going to choose this direction to be positive. Okay, now in doing so, that constrains the other sign conventions. That means moving clockwise here is positive, and moving down is positive. Okay, because if I choose this, because if this moves that way, that moves that way, this moves clockwise. And so if I choose to the right being positive, that means clockwise positive and down is positive. Okay, so that means this tension is positive. So when I do F net equals MA, I get T1 equals M1 A1, which is just M1A. Okay, because again, our accelerations are all the same. All right, so I pause there. I just pause. I have one relationship. I'm trying to find this A, but I don't know T1. Well, let's move to the next object. All right, this is not linear motion, it's rotation, so I need to use Newton's second law for rotation. Okay, now to do that, I'm going to do the pulley here. Okay, so looking at that pulley, I have a clockwise, I have this T1 and or counterclockwise torque from T1 and a clockwise torque from T2. Okay, and they're both at the edge, which means they're different radii and they're both perpendicular. So now using tau equals I alpha, I get, choosing this clockwise one to be positive as I described, I'm going to get force T1 times the distance from the pivot point to where the force is applied, which is R, okay, in sine of theta, but theta is 90. That's positive, minus T1 R equals I of the disk, alpha, but that's I, and alpha would be AT over R. AT over R, but as we just said, that's the same thing as A. So now I can write this T2 R minus T1 R equals I A over R. And now I'm going to simplify that one more step before I move on to analyzing this one. I'm going to divide everything by R, so I have T2 minus T1 equals I times A over R. But what is I for a disk? Well, I looked that up in the table or have it memorized. It's 1/2 M R squared. Okay, that's I. And by dividing this R, I get A over R squared. A over R squared. And it looks like I don't care about that radius in here. That cancels out. So then this just equals a 1/2 MPA. Okay, so now I pause on that one. I've got this relationship here. Now let's go and look at number 2. Okay, free body diagram. I see a tension pulling up. That's T2. And I see gravity pulling down. It should be bigger because it is accelerating downward. Okay, so applying that, okay, yeah, the net force is down. F net, which also means the acceleration is down. So applying that, I get M2G, okay, M2G minus T2 is equal to M2A2, which is just M2A. Okay. Now in drawing this, I just realized I skipped drawing the normal and the gravitational force on this one, which I didn't need for this problem because it was frictionless. I only need the normal force to find the frictional force, but there's no friction force. So I did neglect that, and that's okay in this problem because it's totally useless for the rest of the problem. Okay, we're getting to the point where now we can kind of forget some little pieces that are not important to the problem. Now, if I had to find the frictional force, then I need to draw those normal forces. Okay, now this equation is sufficient to find T2. I have enough information here to find T2 in terms of A. Now remember, A is what we're looking for up here. So I can find T2 in terms of A, plug it in here, and then find T1 in terms of A, plug it in here, and then solve for A. Okay, so in this case, T2, I'm gonna add that to the other side, subtract this over, is going to be M2G minus A. All right, I take that and plug it into here. Then I get M2 G minus A minus T1 equals 1/2 MPA. Okay, solving that for T1, I get M2G. I'm going to go and expand this out because I need to get A by itself. Subtract M2A. So I have multiplied this over, or added this over, subtract this over, and then that'd be a subtract 1/2 MPA. So now I have T1 in terms of A, plug that in here, and I can get M1A, this one right here, okay, which equals T1, equals all of this, equals M2G subtract M2A subtract 1/2 MPA. And then collecting all the A's together, I'm going to end up with A equals M2 divided by M1 plus M2 plus 1/2 MP all times G. And so we need to analyze and make sure this makes sense. If I have a really heavy box, then M2 gets really big, okay? And if it gets big enough, so it's much bigger than the mass of the pulley or the mass of the box on the top, then this pretty much dominates the other ones, and pretty much dominates the other ones, and so I just get A equals G, which would make sense if this is a 1,000-kilogram block of concrete tied to a ping pong ball. Well, it's pretty much just going to fall like it is in free fall. Okay, but if M1 was huge compared, then it wouldn't move very much at all. If the pulley was big, then it wouldn't move very much at all. Okay, but the pulley has less of an effect because it's rotating about a point, and that's not as much energy to do as translation. Now, one thing that's really important is if we assume the mass of the pulley is 0, like we've done in previous chapters, we can cancel this out, and I'll leave it for you to review. In that case, we would just get M2 over M1 plus N2 times G. And so this is accurate with our previous work. Okay, so we have been able to complete this problem and reviewed. This is a fairly complex problem, but we just carefully analyzed each piece with Newton's second law with rotation, and back to Newton's second law, and then worked backwards to find our unknown.